The universe could stop expanding tomorrow and nothing would explode. Stopping expansion means space stops getting larger between distant galaxies. Picture a loaf of raisin bread that suddenly stops rising. The idea matters because timelines for everything would change slowly, not instantly. Gravity and dark energy then contest for dominance over billions of years. That battle shifts how structures move, collide, and cool. For a quick example, distant galaxies would stop receding as they do now. So the immediate picture is a cosmos that stops growing. Close to home, nothing dramatic happens right away. Our galaxy keeps orbiting its center and stars stay bound. Expansion normally acts between galaxy clusters, not inside them, so local gravity dominates. If expansion stops, cluster centers might remain stable for billions of years. Over very long times, gravity could draw neighboring clusters closer, changing group dynamics. For example, the local group will remain bound, and it will not tear apart. So locally, life on Earth faces no sudden cosmic upheaval. On larger scales, the cosmic web would evolve differently. Filaments are vast strands where galaxies flow, making a scaffold of matter. If expansion halts, those flows slow, and gravity thickens the filaments. Matter would move inward along threads, and collisions become more common in dense regions. Simulations predict filament densities rising over billions of years, and mergers increasing accordingly. For instance, a filament spanning 10 million light-years could compress noticeably over long epochs. So the net result is a denser, more interactive cosmic network. The cosmic microwave background would stop stretching further. Background photons lose energy as space expands and they cool over time. If expansion halts, that cooling ends, so photons stop shifting to longer wavelengths. Observed skies would remain relatively warmer than in an ever-expanding case over cosmic times. As an example, photons that would drift into radio bands might linger in the microwave bands for far longer. So the takeaway is that the universe's background glow would dim far more slowly. Astronomers would detect a clear slowdown in recession velocities. Redshift surveys map galaxy speeds versus distance, and trends would flatten. Instruments would measure small deviations, and the pattern would emerge across many observations. Imagine survey data where redshift versus distance curves stop rising and instead level off. For example, a 30-year precision survey could reveal tiny decelerations in distant galaxies. So observers would read a story of cosmic deceleration in the data, not sudden chaos. The leading actor here is dark energy, a repulsive influence on large scales. Dark energy sets the expansion rate, and changes in it alter cosmic motion. If dark energy weakens, gravity may decelerate expansion until it halts. Alternatively, dark energy could flip behavior and become attractive, leading to collapse later. Particle physics allows several scenarios, each with different timelines and signatures. For example, a gradual weakening over tens of billions of years would slow expansion gently. So the mechanism depends on dark energy's unknown properties. A reversal could send the cosmos toward a big crunch slowly at first. Average densities would rise and temperatures climb in crowded regions. Galaxies could collide more often, triggering bursts of star formation and black hole activity. Over extreme collapse, structures would dissolve and matter heats to exotic states. For instance, reversing expansion after 100 billion years could still leave many galaxies intact for a long while. So a reversal produces a hotter, denser destiny, not immediate annihilation. Even a mere stop without reversal changes slow processes profoundly. Star formation would taper, as fresh gas inflows reduce in a non-expanding web. Black hole mergers might grow more common, because encounters increase in denser regions. Long-term energy budgets shift, altering classical heat-death predictions over trillions of years. As an example, galactic cores could dominate visible light instead of faint background radiation after many trillions of years. So stopping expansion reshapes cosmic timelines rather than causing immediate drama. So the picture is this: stopping expansion rewrites cosmic timelines gradually. We would detect changes in galaxy motions, background light, and structure growth across time. The final fate depends on how dark energy evolves and how gravity responds on the largest scales. If you care about cosmic endings, the important work is precise dark energy measurements now. Remember, the change is slow and our telescopes can trace it. If you found this intriguing, subscribe for more cosmology deep dives.